Think about it for a second. From the speed of a car, to the growth of a company, to the orbit of a planet, one thing is totally constant. Everything is changing. Our whole world is in this continuous, beautiful state of flux.
But that brings up a question that's actually kinda tricky. We can easily talk about the average change over an hour or over a day, but what about the change that's happening not over some interval, but at a single, precise instant, right now, at this exact moment? How fast is it changing?
Answering that one question, well, it sparked a mathematical revolution. And today, we're going to build an intuition for what that revolution, calculus, is all about. We'll kick things off by digging into that core problem, then we'll learn the language of instant speed. After that, we'll see what happens when you add up infinite tiny pieces, discover how these two massive ideas are connected, explore why any of this really matters, and finish up with a whole new way of seeing the world around you.
Okay, so let's start right there. The entire field of calculus was pretty much born from trying to solve this one fundamental problem. How do we describe change precisely as it's happening?
Seriously, forget the complicated formulas you've seen. Just for a moment, at its heart, calculus is simply the tool we invented to get past those vague averages and actually measure the rate of change precisely at any single given moment. It's the language of a world that's moving, not one that's standing still.
So, how do we actually speak this language? Well, the first key piece of vocabulary we need is the derivative. That's just the mathematical word for an instantaneous rate of change.
Let's make this super real. Take a look at this graph. It was generated from a motion sensor, and it shows a person's position over a few seconds. The vertical axis, that's their distance from the sensor, and the horizontal axis is just time. So we can see where they are, sure, but how in the world could we figure out their exact speed at, say, the 2-second mark? Right at that one. The big idea here is it's just breathtakingly simple. If you zoom in on any curve, far enough, it eventually starts to look like a straight line. And calculus does exactly that. It zooms in on a single point in time until that curve of motion basically becomes a line. And the steepness, or what we call the slope, of that tiny little line segment, that is the speed at that exact instant. And you know what's amazing? You already have an intuition for this. Think about a road trip, right? Your average speed is just the total distance you drove divided by the total time it took you. Easy enough. But your instantaneous speed? That's what your speedometer is showing you at any given moment. A derivative is basically a perfect mathematical speedometer for any system that changes.
So the crucial takeaway here is that a derivative isn't just some static number. It's more like a crystal ball. It doesn't just tell you what's happening right now. It gives you a perfect model for how that system is going to change in the very next instant. It's the ultimate tool for understanding momentum.
Okay, so derivatives are all about breaking things down into these instantaneous moments of change. But what if we want to do the opposite? What if we have all those tiny moments of change and we want to add them all up to see the big picture? Well, this is where the other half of calculus comes in, the integral.
To build our intuition for this, let's start with a classic problem, a fun one. We all learn in school that the area of a circle is pi r squared. But why? Is there a way to figure that out from scratch? It turns out the answer is a really beautiful introduction to how integrals work. The key is to stop seeing the circle as a single shape and instead see it as the sum of infinite tiny pieces. Imagine slicing it into countless paper-thin concentric rings, like the rings of a tree. Now, just take one of those rings. If we were to cut it and lay it flat, it's pretty much a perfect rectangle. Its length is just the circumference, 2 pi r, and its width is that incredibly tiny thickness, which in calculus we just call dr, a little symbol for a tiny sliver of the radius. So, what happens if we do this for every single ring, from the very center all the way out to the edge?
Well, if you could stack all of those unwrapped rings, from the tiniest one at the center to the biggest one at the edge, they would form a whole new shape, a triangle. The base of this triangle would be the circle's full radius r, and its height would be the circumference of that biggest outermost ring, 2 pi r. Now, just think back to geometry class. The area of a triangle is 1/2 base times height. So if we plug in our values, we get 1/2 times r times 2 pi r, which simplifies to pi r squared. We just proved the area of a circle by adding up an infinite number of pieces. That is the magic of integration. And this right here leads to what might be one of the most beautiful and just mind-blowing ideas in all of math. This relationship between a shape and its rate of change is a fundamental pattern of the universe. The rate a square's area grows, its derivative, is its perimeter. The rate a cube's volume grows is its surface area. And as we just saw, the rate a circle's area grows is its circumference. The derivative of a thing is its boundary. Just let that sink in for a second. This incredible relationship we just saw between a shape and its boundary, it's not a coincidence. It's actually hinting at the most important idea in all of calculus, the deep, beautiful connection between derivatives and integrals. So here's the bottom line. Imagine you have a function that's tracking a total amount, like the total distance you've traveled on a trip. Its derivative gives you the rate of change. That's your speed at every single instant. But if you start with your speed at every instant and you add up all those tiny moments of travel, in other words, you take the integral, you get right back to the total distance you traveled. They are perfect inverse operations. They undo each other. Here's a great way to think about it. Differentiation is like taking a plate and just smashing it into a million tiny shards. You're analyzing the rate of change at every little point. Integration is like being given that pile of shards and figuring out the original shape of the plate. One breaks things down, the other builds them right back up.
Okay, this is all fascinating as a kind of mental exercise, right? But why has this idea become one of the most powerful tools ever invented by humanity? Why does calculus actually matter?
Well, it matters because the world isn't static. Without calculus, we couldn't accurately describe the orbit of a planet or the path of a rocket. We couldn't model the growth of a virus or the returns on an investment. The AI on your phone, the incredible graphics in video games, the complex simulations used to design new medicines, all of it, every last bit, is built on this one fundamental idea of understanding change.
So let's bring this all together. The goal today wasn't to teach you how to do calculus, but to change how you see it. It's so often presented as this huge wall, this intimidating barrier of advanced math. But it's not. At its core, calculus is really just applied common sense. It's a way of thinking with precision about how things change from one moment to the next. It's a lens that just sharpens our view of reality. So the final question isn't about equations at all. It's about perspective. What part of your world could you understand better with a lens that sees not just static objects, but the beautiful, continuous flow of change that connects everything?